Okay, everybody. So what we're going to be looking at today is the Exam 2 practice problems. So you can get these from the modules page, week 5, and then lectures for week 5, Exam 2 info. Of course, the solutions will be posted here, so if you can find this video, then you should also find the documents since they're on the same page. All right, let me download this. Here we go. So this doesn't cover very many, it covers chapter 3 and part of chapter 4. We will see what there is in here. So there'll be a mix. Let's look here at our book before we kind of get started. Calculus, volume 3. So looking in here, this is going to cover sections 3.1 up to whatever's already due. So I think that's 4.5 or 4.6 actually, I think. Maybe. Something like that. Yeah, everything before maximum and minimums. All right, so let's just jump into it. I think we took enough time. Yeah, let's get started. Actually, what I want to do is let's send this over to the Note app. Sorry about that. I didn't think about doing it this way. I was just going to write them from scratch, but let's do this. All right, import that. Done. Where are you? There you are. Okay, so we will do them here. So let's go ahead and get started then, and let's see what we're doing. So first thing we're talking about is level curves. So level curves is when you set a function equal to a constant and you get a curve for where that function is equal to that constant. So on this one it says find equations for level curves f of 0, f equals 0, f equals 1, f equals 2, f equals 3. So you take the function f of x, y equals square root y minus 2x plus 5, and we are going to set that equal to 0. Okay, and then this is something that you would have to solve. So you solve this equation. So you would square both sides. Then you would rearrange it, move the 2x and the 5 over to the other side. You have y equals 2x minus 5. So that's the equation of a line, right? Then we do the same thing for the others. So for f equals 1, you'd have 1 equals square root y minus 2x plus 5. Square both sides. You're going to have y equals 2x, and we are subtracting 5 from the 1 that's already there. So I guess 2x minus 4. 2 square root y minus 2x plus 5. So square both sides, we get 4 equals y minus 2x plus 5. So we have y equals 2x minus 1. And then finally, if we put a 3 in, 3 equals y minus 2x plus 5. Square both sides. Square both sides, I said. And you get y equals 2x and looks like plus 4. 4. Okay, so those are your level curves. Then it says plot them. So these are just straight lines. They all have slope 2, and then they have different y-intercepts. So like the first one here, y equals 2x minus 5. So we go, let's say 1, 2, 3, 4, 5. There you go. And then the slope is 2, so, go through there. And then I'll just kind of draw this line. I mean, I'm not sure how perfectly I'll draw it, but something like that. and that is the f equals 2. I said 2, I wrote 0. 0 is correct. That's the f equals 0 level curve. Then you have the next one here, y equals 2x minus 4. Okay, that's easy. That's the one line up. 1 unit up, I should say. This one's not really in the correct place here. Okay, good enough. So this is the f equals 1 line. Then you have the f equals 2 line here, y equals 2x minus 1. So that one goes through this point. So that's the f equals 2 line. And then finally the f equals 3 line is y equals 2x plus 4. 1, 2, 3, 4 up here. Right. F equals 3. So those are the level curves. Yeah, those are the level curves. The end. What's next? So then we have to find partial derivatives with respect to x and y. So we've got y equals, or f of xy, sorry, equals square root y minus 2x plus 5. So the partial of f with respect to x is going to be, well, we're taking the derivative of something to the 1/2 power. Square root, so it's be 1 over 2 square root y minus 2x plus 5 times the derivative of what's inside with respect to x. So the derivative of what's inside with respect to x is -2. So that's it. You can simplify it. You can cancel those 2's. And we did that. Do the same thing for df dy. So df dy will be 1 over 2 square root y minus 2x plus 5 times the derivative of what's inside with respect to y, which is 1. So that's it. We're done. And those are, very straightforward derivatives. Problem 1 done. Okay. Evaluate the limit or show that they do not exist. So there was more of this in the lecture than there was in the homework because it's hard to do these on the homework. On the real exam, remember your real exam will be multiple choice and so on. So, maybe that makes it easier. But the thing to keep in mind about these is that it's really hard to show that the limit exists if it's not continuous. So if you had something like this, for example, 1 x squared, let's say, to make it easy, x squared plus y squared, right? If you had something like this, x, y approaches 1, 1, all you would do is you would just plug in 1, 1, and you get 1 squared over 1 squared plus 1 squared. And you would be able to do that just because, just because it's a continuous function, right? There's nothing stopping you from plugging in the 1, 1. All the numbers near 1, 1 are able to be plugged in here, right? There's no divide by 0 or anything to worry about. Yeah. I don't know why I was looking at the frame rate. It's all bad, and I don't really know why. But I'm not going to worry about that right now. Okay, so what can we say about this? Yeah, okay, so if we could plug in the numbers, we would just plug in the numbers. That's kind of the punchline there. Now, on this problem, you can't just plug in the numbers because hopefully you can see that if you do try to plug in the numbers, you're going to get, 3, 0, 0 over 0 minus 0, which is 0 over 0, and that's undefined. So you can't just plug in you can't just plug in 0, 0. Does that mean the limit doesn't exist? No, not necessarily. You would have to try to approach 0, 0 along many different paths. And so what I mean by that is 0, 0 is somewhere right here. So you can try to get to the 0, 0 along a straight line or along a different straight line. That's not a straight line. Along a different straight line. You could try to approach along a parabola. That's a way to do it. Or any kind of way you want to get to 0, 0. So generally what you do is not show that the limit exists. Normally you show that it does not exist by trying to take the limit along different paths, and then those paths give you different answers. So I'm going to try this. I'll say approach, let's see, 0, 0 along the line. How about y equals, let's just do y equals mx, right? A straight line through the origin, right? It needs to go through the origin because it has to go through 0, 0. So what would that look like? Well, we would take our limit. X will just be x. The y will be mx. 0, 0. And then we're going to plug in y equals mx. So the y on top is mx. And then on the bottom, the y here is mx. And the x is just x. Okay, so I don't know why I put a 2 there. It should be a 4. So this is what we get when we plug in mx for y. So we're going to try to evaluate this. We get limit. There's only x now, so I can just write it that way. On top, it looks like I've got 3m x cubed. On the bottom, I've got 5m squared x squared minus x to the 4th. Okay, and we got to figure out what happens to this limit. And just from looking, I can see that what's going to happen here is that that this limit is not going to exist. You can do L'Hopital's rule, or we can do a little bit of algebra. So a little bit of algebra here. There's different ways you could do it. You can divide every term by x cubed or x squared or x to the 4th. I think what I want to do is divide every term by x squared. We'll try that. So if I multiply by 1 over x squared, that'll be a 0 there, and then on the bottom I'll get it'll be fine. Over 1 over x squared. So basically divide everything by x squared. So when I do that, what I'm going to get is that I'm going to get like 3m x to the 3 over x squared, 5m squared x squared over x squared minus x to the 4th over x squared. Cancel all the x's that you can, and you get 3m on top, 3mx on top. On the bottom, you have 5m squared, and then x squared over x squared is 1, and then minus x squared. So now what happens when x goes to 0 here is that you're going to get on top 3 times m times 0, which is 0, over 5m squared minus 0. So you end up with 0. You end up with 0. So that makes it look like the limit might be 0. Okay? But that's not enough to show that the limit is 0. What you'd have to do is maybe take a different path. So let's try to approach along a different path. Maybe we try to approach 0, 0 along y equals, let's say, kx squared, parabolic path like this one. K is just a constant. Then what will happen is we will have the limit as x comma kx squared approaches 0, 0 of, what is it? It is 3x squared y, 5y squared minus x to the fourth. Like that. So we're going to put in our, I didn't replace the things. So let's actually replace the y's with what they are. So we have 3x squared kx squared. Okay. On the bottom, we have 5kx squared squared, and then minus x to the fourth. Okay. So far, so good. Work these all out. On top, you've got a 3, a k, and an x to the fourth. On bottom, you've got a 5, a k squared, x to the fourth minus x to the fourth. So everything here is over an x to the fourth. So if I multiply everything by 1 over x to the fourth, I'm going to get, well, I'm going to be a little bit lazy here. If you do what we did on the previous part where we divided everything by x to the fourth, basically the x to the fourth will cancel that one, and this one will cancel both of those, and you'll be left with 3k over 5k squared minus 1. I said 5k squared, but I wrote x squared. 5k squared minus 1. Then when x goes to 0, you get 3k over 5k squared minus 1. Now, generally, k is not 0. So this is actually, this is not generally 0, right? Because k is not 0. And also, it's, different values of k give you different limits, right? If you plug in k equals 0, you get 0. If you plug in k equals 1, you get like 3 over 4 or something. Different k gives different limits. So what does that mean? That means that along one path, you get 0 for the limit. Along another path, you get something different. And actually, we could have just done this. Every different k gives you a different limit. So if there's supposed to be one limit, there isn't. So we would just say that this limit does not exist. So since different limits, you get different limits when you approach 0, 0 along different paths, there is no limit. So this limit does not exist. Okay. B. Let me look at it. Okay, so this is what I was talking about on the previous one, where I said if you can just plug it in, then it's going to be a continuous function here. No divide by zeros, nothing like that. Then just plug in the numbers. So we got 2 minus 0 to the 3, 5, 0 squared minus 0 plus 3. So you get on top 8 and on the bottom 3. That's your limit, right? When you do the limit of a continuous function, you just have to plug in the point. Done. That's why the first thing we did up here, which I erased, was just checking if we could do that. Right, problem 3. How many problems is this, by the way? Just to see how to split the video. 9, so if we can do 5 maybe. Problems. All right. Here we go. Consider the space curve given by this. So this is, you could write it, you don't have to write it in that notation. You could write it in this notation, 1, 2t, 2t to the 3 halves. that would be fine as well. I usually write it that way. I only use the IJK notation just because you do need to be familiar with both, but you can use whatever you want. All right, r prime of t, well, that's just taking the derivative with respect to t of each of these individual components. So very simple. The derivative of 1 is 0. The derivative of 2t with respect to t is 2. And the derivative of 2t to the 3 halves with respect to t, well, you bring the 3 halves down in front. You get 3t. Subtract 1. 3 halves minus 1 is 1 half. And there you go. Part B, find the magnitude of r prime. Well, we just found r prime, so the magnitude is straightforward. It's the magnitude of a vector. So it'll be the square root, and you just square each component and add them. So 0 squared, 2 squared, 3t to the 1 half squared. So the magnitude is the square root of 4 plus 9t. There you go. Find the length of the portion of the curve that lies between the points where t equals 0 and t equals 1. Okay, so how do we do that? Let me just go here. So if you look in the section 3.3 for arc length, then you will simply find formula. So kind of the key here, hold on, or the not really the point, but just kind of an idea is so here's an example, and it says like S, which will be arc length S equals integral from a to b of square root f prime squared plus g prime squared plus h prime squared dt. The point is that if you think about that formula that I just wrote there, this is the f prime, g prime, h prime. This is the square root. So like the magnitude of r prime here is this formula. So like the arc length S is equal to an integral from a to b of the magnitude of r prime dt, like that. That's why I had you calculate those ahead of time. So if we're going to do r's, like our actual problem, the arc length is going to be, that's just an S. It doesn't even look like an integral symbol. A to B are given to be 0 and 1. And then our magnitude of r prime is what we just calculated, 4 plus 9t dt. So that's it. We just have to do this integral now. And so this is just, do you remember how to do integrals from Calculus 1, right? So this is a, you would normally do this integral with a u substitution. So you would say something like u equals 4 plus 9t. Du would just be 9 dt. So, dt is du over 9. So then your integral is the integral of u to the 1 half, right? That's the square root. And then du over 9. That's our integral. But we can also change the limits of integration, because if you plug in t equals 1 into the u equation, you're going to get u equals 4 plus 9 times 1, which is 13. So you can replace this top limit where t equals 1 with u equals 13. And when t is 0, u is 4 plus 9 times 0, which is 4. So you can replace the t equals 0 limit with 4. So this is our integral, and then we just do this integral. So we have 1/9. The antiderivative of u to the 1/2 is u to the 3/2 over 3/2. And we're evaluating between 4 and 13. So this is, of course, 1/3 u to the 3/2 from 4 to 13. What can we do? I guess I could take out, I don't know why I put 1/3 there. That should be 2/3 there. So this is actually 2 over 27 if I take the 2 and the 9 and the 3 together. And then my u here is going to be 13 to the 3/2 minus 4 to the 3/2. And you can simplify 4 to the 3/2, but the rest of it won't simplify. So I would just stop it here. And the arc length is done. So point is, you have your arc length integral here. Really sorry about the chop here. I think it's OBS is causing me some issues. All right, let's look at this one. A shell fired from a gun situated on a hill 400 feet above ground level with a muzzle velocity 300 feet per second, angle of 45, use 2D vectors. Write out the vector AT. Hint, it's just gravity. So what's gravity for feet, right? I think it's going to be like negative 32 feet per second squared, right? Of course, you just look that stuff up if you forget. So you just go like 32 feet per second squared. So what's A of t? So if we think about this as a vector, which I say to use like 2D vectors, so we're thinking of the situation where you've got an x-axis and a y-axis, and the AT vector, well, there's no acceleration in the x direction due to gravity, but there is an acceleration down by negative 32, and that's in feet per second squared. All right. Now it says part B, find or write out the vectors for the initial conditions for v of 0 and position. So the idea here is, if you remember, we're just going to look up that the situation is we're starting out 100 feet above level ground. So we're starting up here at 100. This is our starting position, right? And we are aiming 45 degrees up this way. Okay. So our initial position is 0 in the x direction, right? Assuming that this is 0, but in the y direction, we're starting 100 feet off the ground, right? Now, for your initial condition for velocity, we need to get from the fact that this is a 45-degree angle. And so you just think about drawing a little triangle on here, like this. And the idea is that when we say that the muzzle velocity is 300 feet per second, that means this is 300. And then this is 45 degrees. And then based on the geometry or trigonometry of this situation, this side is going to be 300 times the sine of 45 degrees. And this side will be 300 times the cosine of 45 degrees. Now, of course, sine and cosine of 45 degrees are root 2 over 2. So what we get there is that the x, which is the 300 cosine 45, is going to be 300 square root 2 and then over 2, right? Square root 2 over 2. And then the y direction is going to be 300 sine of 45 degrees, which is also square root 2 over 2. I don't know what my brain was doing there to make that take a long time. But there we go. So these are what we get. So find the velocity of the shell. And there are formulas for all this stuff, by the way. Oops, popped my knee. So there are formulas for all this stuff that you can use, but I'm just kind of deriving it as we go here. So in order to get velocity, you integrate acceleration. So like you can say like v of t is going to be, well, you're going to integrate the velocity, which is, sorry, the integral of at. And we're going to have to do something with our initial condition as well, but we will do that in a minute. So yeah, sorry. So we have the integral of a of t. Where's a of t? Oh, up here. 0, negative 32 dt. So your velocity is, you take the antiderivative here, antiderivative of 0 dt is going to be constant, right? I'll just put like c1. And then your antiderivative of negative 32 will be negative 32 t plus a constant like this. And yeah. And then we use our initial condition, v of 0 equals what it's supposed to equal, and that will give us the final velocity equation, right? So we use the fact that v of 0, which is, I'm going to plug 0 in here, is going to be c1 negative 32 times 0 plus c2, and then we move this. That'll work. V of 0 is known to be 300 square root 2 over 2. I'm going to simplify that actually a little bit. Of course, 300 over 2 is 150, right? So 150 root 2 and 150 root 2. So what that tells you, if you think about it, is it's just telling you that the C1 comma C2 is just 150 root 2, 150 root 2. So what do we get? Well, fill those in to your velocity equation, and you get that v of t is 150 root 2, comma, negative 32 t plus 150 root 2. Okay, so we have v of t. Then they say find the position equation for the shell. Well, to get the position equation, then you have to integrate velocity. So we have that the s of t, is the integral of the v of t dt. So it's going to be the integral of 150 root 2, comma, negative 32 t plus 150 root 2 dt. So we integrate this with respect to t. So we're going to get 150 root 2 t and negative 32 t squared over 2 plus 150 root 2 t, like that. I didn't put my constants. I should have, on this one right here, I put my constant there and there inside of this when I integrated. I should have done that here, but I didn't. So I'll have to put them at the end here like this, C1, C2. And there we go. Now, then what we need to do is we need to find that C1 and C2 using the initial velocity of, using the initial position of the shell. So we know that S of 0 is going to be, well, let's plug it in here, 150 root 2, 0, comma, negative 32, 0 squared over 2. I should have, simplified that, but I didn't. It's fine. Plus, this is a different C1 and C2 from the previous problem. We have that. So S of 0 is, according to this, this entire vector just zeroes out because everything had a t, so everything has a 0. So S0 is just C1, C2. But of course, F0, which is C1, C2, we found in part B that it should be 0, 100, right? So it should be 0, 100. 0, 100. So we have the C1 and the C2 there. So finally, I can write that my S of t, ST, is going to be my ST that I found, which is 150 square root 2t plus the C1, which is 0, so I don't have to write it. And then the other one is going to be negative 32t squared over 2, which is negative 16t squared, plus 150 square root 2t, and then plus C2, which is 100. So there's my position equation. Okay, and again, there are, if you look in the textbook, you could have taken some shortcuts where there's formulas for these things, but we just did it by integration. What is the shell's maximum height? Right, so of course the point is that we're starting at 100 here and we're aiming up, so it goes up and then it comes down and then it hits 0. But the question is, what is its maximum height? So of course the maximum height is right here, and so what we need to think about is I'll put a capital T, so I'm going to call that capital T there. So at t equals capital T, the y component of velocity should be 0. Why? Because it was going up here and it's coming down, so velocity must have gone through 0. That's not the total velocity is 0, that is the velocity in the y direction. So you come up here to velocity, and we've got right here, this is the y component of velocity. So I'm just gonna steal that, duplicate it. Here's the y component of velocity, oops, too far, right here. And we are just going to set this equal to 0. And we solve that. So we have 150 square root 2 equals 32t. And then divide by 32. T is 150 square root 2 over 32. Does that reduce? We'll find out. 150 over 32. $75 over 16. That was not as much as I was hoping for. All right, but 75 root 2 over 16. All right, so that's the time. That's not what it asked. it asked for what is the shell's maximum height. So what we have to do then is compute the y position at this time. So position, remember, is the S of t equation at t equals 75 square root 2 over 16. And yeah, so that's what you have to do. So position equation is here. Here's the y component of the position equation. Duplicate. Oops, too far again. So we have to take this. This is S of t. Y component of that, actually. So I'm going to call it y of t. And we just need to plug that number in. So we just need y of 75 root 2 over 16, negative 16, 75 root 2 over 16 squared, plus 150 root 2, I'm out of room, 75 root 2 over 16, plus 100. You know, a lot of times what I'll do on these is I'll write it out like this, like I was going to do it on a calculator or something. And then I jump to like Wolfram Alpha. And what I like to do is you can type in a function. I recommend, if you can, just use F, because it gets confused about function names sometimes. Like you'll use a function name because they used it in the problem, but then Wolfram Alpha will think, oh, because you used a G, you must be talking about this famous equation G. So anyway, 16t squared, 150 square root 2t plus 100, that's the function. And then I'll just say at t equals 75 square root 2 over 16. And we get our answer to be 6425 over 8. That would be feet. Notice they also gave us a nice picture here, right? You can see our curve, our parabolic curve here. The x-axis is not correct because we only put in the y equation, but the y component is correct here. So yeah, there you go. Just over 800 feet. All right. 5:24, we're 43 minutes in. So one more question, and then that'll be it for part 1 here. Yep, that's good. What do we do? All right, so we got a function of 2 variables now, and we're looking for partial derivatives. So there's nothing, you know, no mysteries here. We just need to find these partial derivatives just to make sure we can. So what do we do? So fx partial with respect to x of x squared sine 5y squared. Of course, what you should notice about this is the only x. So as far as the partial with respect to x is concerned, the sine 5y squared is just a constant. So 2x sine 5y squared. There you go. Now we need to find fy. Fy is what the partial with respect to y of x squared sine 5y squared. Again, we're taking the partial with respect to y, but this is the only part of the function with a y in it. So we get x squared, and then the derivative of sine is cosine 5y squared, and then the derivative of what's inside for the chain rule, the derivative of 5y squared with respect to y is 10y. So there you go. you can simplify that if you want. So 10x squared y cosine 5y squared. There you go. All right, now it wants the mixed partial derivatives. The mixed partial derivatives. So for mixed partial derivatives, that means take the derivative of the like fxy, that's going to be the partial with respect to y of fx, right? So we're just going to take the partial with respect to y of the x derivative and take the partial with respect to x of the y derivative. So if we do the partial with respect to y of fx, which is up here, 2x sine 5y squared, then the only place where there's a y is here. So we get 2x, and then the partial with respect to y. Wait, yeah, okay, that's fine. Cosine 5y squared times the derivative of what's inside, which is 10y. Okay, so this is 20xy cosine 5y squared. That's f of xy. Now, I also ask for fyx, and the point there is that these should be the same. fxy and fyx should be the same. But we'll find out because we have to do it. So we want the partial with respect to x now of fy. Doing fxy. No, fyx. So partial with respect to x of fy, which is 10x squared y cosine 5y squared. And the only place where there's an x is right here. So the partial derivative of 10x squared is 20x. So you have 20xy cosine 5y squared. There's that one. And of course, the point is that this and this are the same. Okay. All right. Next, fxx. So we have fx is up here, still that. So there's, oh, disappeared on me. So we have fx. So we need fxx. fxx will be the partial with respect to x of the partial with respect to x. So again, there's only x's right here. So the partial with respect to x there is going to be 2. So you get 2 sine 5y squared. All right. Problem done. Okay, so that's 48 minutes. So we're going to stop right there. In the second video, we'll look at the rest of these problems. So this is going to be solutions part 1. Okay, so that's it for now. Talk to you guys later.